Welcome back to AI Paper Podcasts. Today we're diving into something pretty challenging in AI formal theorem proving.
It really is. We're talking about getting AI to do math proofs with absolute verifiable rigor.
Yeah, the kind of deep, structured reasoning that, honestly, large language models haven't always been great at, requires precision, step-by-step logic.
Exactly. LLMs are amazing at generating human-like text, finding patterns, even informal reasoning sometimes, but proving something line by line in a system like Lean 4, where every single step has to be checked by a computer.
That's a whole different ballgame.
Totally. It needs a level of logical strictness that's been, well, a real hurdle. Traditional AI provers often lean heavily on these big, computationally expensive search algorithms.
Kind of like brute forcing the proof.
Sorta, yeah.
Yeah.
Searching through tons of possibilities. And, a big frustration in the field has been that just making these models bigger didn't always mean they got reliably better at this specific task.
Right, the scaling wasn't quite there, which is exactly why this new paper we're looking at today is so interesting.
It's a technical report called Kimina-Prover Preview towards large formal reasoning models with reinforcement learning. And it's from the Numina and Kimi team.
And they're proposing something pretty different. A new paradigm they call reasoning-driven exploration.
Reasoning-driven exploration. Okay,
Yeah.
What does that mean in practice?
Well, it's a really significant shift. Instead of relying on a separate external search process to figure out the proof steps.
Which sounds computationally heavy.
It can be, yeah. Instead, their Kimina-Prover model uses its own internal reasoning capabilities. It's guided by a specific way it formats its output, and this internal process implicitly explores a problem space to actually derive the proof.
So the model's own, thought process is the exploration.
You got it. The model's thinking is the search, in a way.
Okay, interesting. So it's not just guessing steps for another system to check. It's actually figuring out the path internally. How did they make that happen?
They put together this really large-scale reinforcement learning pipeline. They started with a very powerful base model, Quinn 2.572b. Okay, the 72 billion parameter one.
Yeah, and they combined that RL pipeline with this unique structured output format. They call it the formal reasoning pattern.
All right, let's pause there. Before we dive deep into that pattern and the pipeline, can you give us the quick, 1-minute version, the key takeaways for folks tuning in?
Absolutely. Let's do the nutshell version. Start a 1-minute summary. So the core problem. Formal theorem proving, say in Lean 4, is super important for verifying things like complex software or math concepts, but it's really, really hard for AI. Current methods often need costly search algorithms and haven't consistently improved just by getting bigger. So the core problem, the solution presented here, is Kimina-Prover Preview. It's an LLM trained using a new idea called reasoning-driven exploration. This involves a big RL pipeline built on Quinn 2.572b and uses a special formal reasoning pattern for its output. So the core problem. And the results. Well, they're pretty striking. It hits state-of-the-art on the mini F2F Benchmark. That's 80.74% pass at 8192. It's also really sample efficient, getting good results even with just one try. And maybe most importantly, it shows clear performance scaling with model size from 1.5b up to 72b. That kind of scaling hadn't really been seen before in neural provers for formal math. Plus, it blows general-purpose LLMs out of the water on these formal benchmarks. So the core problem. End of 1-minute summary.
Wow, okay. That summary definitely packs a punch. SOTA, sample efficiency, and that scaling with size. That scaling bit is really sticking with me because, like you said, it bucks the trend.
It really does. It suggests something fundamental is different here.
So let's dig into how they did it, starting with that formal reasoning pattern. What does that actually look like? How does it structure the model's thinking?
Right. So it's actually designed to kind of mimic how a human mathematician might work through a proof. The model outputs text structured with these specific tags, think and think.
Okay, like XML tags.
Sort of, yeah. And inside those tags, the model generates informal, natural language reasoning. It might break down the problem, talk about potential strategies.
Yeah.
Basically like the notes you or I might scribble down when tackling a hard math problem.
Makes sense.
But crucially, this natural language thinking is interspersed with actual Lean 4 code snippets.
Ah, okay. So it might output something like, inside the think tags, okay, my goal is to prove this function is continuous. That means for any epsilon, there's a delta. Maybe I should start by fixing an arbitrary epsilon greater than 0. Let's write that down in Lean. Fix deme a, assume arimo, something like that.
Exactly like that. It's literally laying out its strategy in the formal steps side by side. And there's a key constraint they trained it with. Most of those lean code snippets inside the think block, they actually have to appear in the final formal proof it generates.
Oh, interesting. So the thinking isn't just idle chatter, it has to directly inform the final outcome. What's the benefit of forcing this structure?
Well, there are quite a few big upsides. First, explainability gets a huge boost. You can actually read the think block and trace the model's reasoning. It's way more transparent than just looking at a sequence of cryptic tactic calls.
Right, you can see why it tried a certain step.
Exactly. Second, that transparency really helps with debugging. If a proof attempt fails, you can often look at the thinking part and see, okay, that's where the logic went off the rails.
That makes sense.
Third, they suggest it could actually be a pretty good educational tool. Showing students a model working through the process of constructing a formal proof.
I can see that.
And they notice something really interesting in their results. The average length of the model's output, including all this thinking, directly correlated with solving harder problems.
So more complex proofs required more thinking steps.
It seems so. More complex problems seem to need more extensive internal reasoning, more planning captured in that format.
That feels pretty intuitive, actually. More planning for harder tasks.
Okay.
So that's the pattern. But how do you actually train a beast, like a 72 billion parameter model, to follow this complex pattern and produce correct, verifiable lean proofs? The training must be pretty complex, especially, like you hinted, given the lack of huge data sets of formal proofs in lean.
Yeah, data scarcity is a massive bottleneck in formal math AI. They had to be quite clever here. First step, they needed more formal problems to train on. So they developed their own model called Camina Autoformalizer 7B.
An autoformalizer, so translating natural language math problems into lean code.
Exactly. Taking something like an Olympiad problem statement written in English and turning it into a formal lean 4 theorem statement.
But wait, auto-formalization is notoriously tricky, isn't it? Like, how do you know the lean code actually means the same thing as the original English problem? Checking if it compiles is easy, but checking semantic equivalence.
That's the million-dollar question. You hit the nail on the head.
Yeah.
Verifying semantic correctness is the core challenge. Their approach was this structured, iterative process involving human expertise, LLM expertise acting as a proxy. They started by supervised fine-tuning the autoformalizer on known pairs of natural language and lean problems.
Okay, the standard starting point.
Right. Then they went into this loop. They'd generate new formal problem statements, check compilation, and then, this is the clever part, use a separate LLM as a judge. Specifically, QWQ32B with very carefully designed prompts.
So one LLM judges another LLM's translation.
Essentially, yes. The judge LLM's job was to assess if the generated lean code accurately captured the meaning of the original natural language problem. They refine this process over several iterations, and they show in Figure 5 of the report how this steadily improved both the rate at which the generated code compiled and its semantic accuracy, according to the judge.
Okay, that's a neat solution to the correctness problem for generating data. So they build this robust autoformalizer to get more training problems. What's next for training Kimina-Prover itself?
Then comes the main training sequence. It starts with Supervised Fine-Tuning, SFT. They collected a data set of Olympiad-style problems that already had both natural language solutions and corresponding formal lean 4 proofs.
Got it.
Then they used another LLM, Claude 3.7 Sonnet in this case, to help generate those crucial think blocks for about 20,000 of these examples. This SFT phase is really about teaching the model the structure, the grammar, if you will, of that formal reasoning pattern.
So learn the format first.
Exactly. And critically, they also mixed in data from another model, Kimi K1.5, which contained examples of informal mathematical thinking. This wasn't formal proof, just general math reasoning.
Why add informal thinking data?
They found it helped improve the quality of the reflections the model generated within the think blocks during the later main training phase, made the thinking more insightful, more human-like.
Interesting. So SFT sets the structure and primes the thinking quality. Then comes the reinforcement learning part.
Yes, that's the core training loop, starting from that big Quen 2.572p model. It's iterative, like you'd expect with RL. You sample a batch of problems, maybe 1,000 or so. The model tries to solve them, generating outputs in that formal reasoning pattern.
Right.
Then you extract just the lean 4 code part, send it off to a verifier, basically, the lean compiler.
To see if it's a valid proof.
Precisely. And you assign a simple binary reward. 1 if the proof compiles correctly, 0 if it fails.
Okay, clear reward signal. But RL, with these huge models can be notoriously unstable, right? Did they have trouble keeping the model sticking to that specific formal reasoning pattern structure during RL?
Oh, absolutely. That was a major challenge they detail. They encountered something they call format collapse.
Format collapse.
Yeah, where the negative gradients you get during RL training, the signals telling the model that didn't work, could actually cause the model to just stop using the think tags or the lean snippets correctly. It would drift away from the desired structure.
That sounds bad. If it loses the structure, the whole reasoning-driven idea falls apart.
Exactly. So they had to implement specific techniques to combat this. One was format filtering. They basically checked the generated outputs to make sure they still contained tactic blocks, and that these blocks made up a reasonable percentage of the code.
Okay, enforcing the structure.
Another technique was to randomly discard some training samples that produced negative gradients, with a certain probability, about 50%, parameter 0.5. This prevented the negative signals from overwhelming the model's ability to maintain the format. These tricks, combined with that strong initial SFT that included informal math thinking, were really key to stabilizing the RL training. It allowed the model to get better at reasoning without forgetting the structure.
Preventing format collapse sounds absolutely crucial. You mentioned sending proofs to the lean compiler for verification. Isn't checking formal proofs usually quite slow? How did they handle that efficiently for large-scale RL?
That's a very sharp point. Verification speed is often a huge bottleneck. They actually built a custom lean server just for this training pipeline.
Ah, specialized tooling.
Yeah, it uses caching very effectively and is highly parallelized. They reported getting verification speeds up to 100 iterations per second.
Wow, 100 checks per second.
Yeah, which is pretty fast. And maybe even more impressive, they did this on relatively modest hardware. They mentioned needing only about 640 CPU cores in total for handling all the verification during the training rollouts.
That's surprisingly efficient compared to some other systems.
It really is. Some previous setups needed thousands of cores just for the verification part. Making the step efficient was absolutely vital to making the whole RL training loop practical at the scale of a 72B model.
Okay, so they've got this big, powerful 72B model trained. Did they also create smaller versions, maybe ones that are easier to run?
They did. They used distillation. After the big 72B model was trained, they basically used its successful outputs, the correct proofs, with their thinking steps, as training data for smaller 1.5B and 7B models.
Ah, teaching the smaller models from the big ones examples.
Exactly. They fine-tuned these smaller models using that distilled data, and they started them off from Quen 2.5 Math Instruct checkpoints, which likely gave them a good head start on mathematical reasoning.
Smart. Okay, let's get to the results, the numbers. The go-to benchmark here is mini F2F, right?
That's the one. They used the Lean 4 version specifically. They're pretty careful about methodology. They made sure to decontaminate the data so no test problems accidentally showed up in training.
Good practice.
And they even went through and fixed some problems on the benchmark itself that were apparently unsolvable or stated incorrectly, which is important, right, for reliable evaluation.
Definitely need a clean benchmark. And how did they run the evaluation?
They used a 32,000 token context window, which is pretty generous, and they allow the model to generate up to 8,192 candidate proofs per problem. That's the pass at A2 into 192 means did it solve it within 192 tries.
Okay, 800 and 192 samples is quite a lot. What was the headline number? The pass at 892.
State-of-the-art performance. If you look at Table 1 or Figure 1 in the paper, Kimina-Prover Preview hits 80.74% pass at 8192 on the MIDI F2F test set.
80.74%. How does that compare?
It's a pretty significant jump. The previous best reported result on that benchmark, using BFS Prover, was around 72.95%. So going from just under 73% to over 80% is a substantial improvement in this domain.
Yeah, that's definitely a leap. Very impressive. You also mentioned sample efficiency earlier in the summary. How does that look?
This is where that reasoning-driven approach really seems to shine. The model performs remarkably well, even with very few attempts or samples. Look at these numbers. 52.94% pass at 1.
Over half the problems solved on the first try.
Exactly. And 68.85% pass at 32. Many other approaches need hundreds, maybe thousands of samples to get anywhere near those kinds of success rates.
So why is it so much more efficient?
The hypothesis is that because the model's internal reasoning process is guiding the exploration, it's making more intelligent choices right from the start. It's not just blindly sampling tactics. It's using its learned planning ability from the think process to narrow down the possibilities effectively, sort of flattens the search space implicitly.
Less brute force, more guided exploration. Makes sense. Now let's circle back to that scaling result you mentioned. Figure 3 in the paper apparently shows this clearly.
It really does. Figure 3 is quite striking. It plots the performance, say, pass at 1024 for the 1.5B, 7B, and 72B models. And you see this clear, consistent upward trend. Performance improves significantly as you go from 1.5B to 7B, and then there's another big jump up to the 72B model.
How big a jump?
Well, for instance, at pass at 1024, the 72B model solves nearly 8 percentage points more problems than the 7B model. That's a really strong scaling signal.
And why is that so significant again?
Because, as we discussed earlier, this kind of reliable, consistent performance improvement just from increasing model size hadn't really been demonstrated clearly before neural theorem provers, specifically for formal math. People tried making models bigger, but the gains were often marginal or inconsistent. This result suggests Kimina-Prover's architecture and training method genuinely allows it to use that extra capacity in larger models for better, deeper reasoning.
So for this system, unlike some past efforts, bigger actually does mean demonstrably better reasoning. That's a key finding. How does Kimina-Prover stack up against the big general-purpose LLMs? You know, the ones from OpenAI, Google, Anthropic.
Yeah. Table 2 addresses that directly. It's a night-and-day difference on formal math benchmarks.
Really?
Oh, yeah. Kimina-Prover just dramatically outperforms models like they tested OpenAI O3 and Gemini 2.5 Pro on any F2F and also on subsets containing problems from the IMO and AIM math competitions.
Okay.
Even on problems that the general models might understand conceptually, Kimina-Prover's ability to generate the formally verifiable lean code gives it a huge edge. For instance, on the full mini F2F test set using pass at 32, Kimina-Prover gets nearly 69% correct.
Can the other?
Gemini 2.5 Pro is down around 37.7%, and OpenAI O3 is even lower at about 24.6%.
Wow, that's a massive gap, like not even close. Why do the general models struggle so much with the formal verification part, even if they might know the math informally?
It really comes down to the absolute rigor demanded by formal systems like Lean. General LLMs are optimized to generate plausible, fluent text. And sometimes that includes math steps that sound right but aren't logically watertight, or they contain subtle errors, or they just aren't expressed in the precise syntax Lean requires.
Hallucinations or just not following the rules.
Exactly. Formal verifiers are ruthless. They catch any little mistake immediately. General models often default back to giving an informal explanation rather than a strict verifiable proof. Kimina-Prover, on the other hand, was trained with the lean verifier in the loop. It learned through reinforcement, learning what constitutes a valid, checkable proof. It knows the rules of the game.
That really underscores the difference between just talking about math and actually proving it formally. But the paper also hints that maybe succeeding in formal reasoning could feed back and help with informal math too.
Yeah, that's one of the more, let's say, forward-looking but really exciting implications they touch upon. They observe that general models often solve problems informally but fail formally. Kimina-Prover flips that. Its success suggests that learning within the structured, logical environment of a formal system might instill a deeper, more robust understanding of mathematical structure and deduction.
So learning the formal rules might make you better at the informal game.
Potentially, yes. That deeper structural understanding learned from formal math could, in theory, improve a model's ability to solve informal math problems more reliably. It's this intriguing idea that formal verification training might not just be about proofs, but could be a pathway to building more generally capable mathematical AI.
That's a really powerful potential link. They also tracked performance during training, right? And linked it to how much the model was writing.
Yes, figure 4 shows that. It plots the test accuracy, pass at 32, against the average length of the output tokens the model generated per problem as training progressed.
And what did it show?
It showed a clear correlation. As the model got better, as its accuracy increased over training iterations, it also tended to generate longer outputs, more think steps, more lean code.
So better reasoning meant more verbose, detailed output.
It seems so. The line isn't perfectly smooth, there's some volatility, which probably reflects the difficulty of learning this kind of complex reasoning, especially maybe without massive amounts of purely formal pre-training data. But the overall trend is upward. Longer, more detailed formal reasoning outputs correlate with higher success rates. It suggests this structured reasoning approach can scale with training time.
And finally, they talked about the style of the proofs the model generates. They called it emergent human-like. What's that about?
Right. That's more of a qualitative observation from looking at the actual proofs Kimina-Prover produced. Because it uses that reasoning pattern and the RL rewards success, it tends to generate proofs that have structure. They have statements, for example.
Which humans use to state intermediate lemmas or steps, right?
Exactly. To break down a complex argument into smaller, easier-to-follow pieces, the model shows signs of planning, of considering different cases within its thinking block. They contrast this with the style of proofs you might get from pure search-based provers, like BFS Prover. Those often look like long, flat sequences of low-level tactics, much harder for a human to read and understand the high-level strategy. Appendix E in the paper has a nice comparison.
So it's not just correct, it's also more readable, more structured.
That seems to be the case. They give some specific examples too. It solved part of an old IMR problem, 1968 P5 Part 1, that apparently hadn't been solved by public models before, suggesting strong planning. Appendix D shows Amy examples where it handles tricky trick identities using the CALC tactic for step-by-step calculations, all guided by the thinking pattern.
And that arithmetic sequence example they mention, Appendix D.3, sounds like a clear illustration of the think-then-code pattern.
Yes, it apparently shows the informal thought process directly leading the formal lean steps. These examples really highlight that the model isn't just pattern matching. It seems capable of genuine algebraic manipulation, strategic decomposition, and executing complex calculations within the formal system, guided by that internal reasoning structure.
Okay, so let's wrap this up. Kimina-Prover seems like a genuinely fresh take on formal theorem proving. This reasoning-driven exploration idea, powered by large-scale RL on a model like Quen 2.572BB, and that specific formal reasoning pattern.
It's definitely novel, and the results speak for themselves. State-of-the-art performance, that impressive sample efficiency, meaning it finds proofs faster, and crucially, that demonstration of clear performance scaling with model size. That last one is a really big deal for the field.
Right, and it achieves all this while blowing general LLMs out of the water on formal tasks and producing proofs that seem more interpretable, more structured, maybe hinting at a deeper grasp of logic.
Exactly. The whole package is quite compelling.
What really stands out to me looking ahead are the future directions they mention in the paper. Things like improving the quality of the proofs, maybe filtering out overly complex tactics, making them cleaner.
Or enabling iterative refinement. Imagine the model tries a proof step. The Lean compiler says, nope, error here, and the model actually uses that feedback to backtrack and try a different logical path. Like how a human debugs a proof.
That would be incredible. And integrating external tools too, letting it call out to a library search tool or maybe a computer algebra system for heavy computation.
It really opens up possibilities, and it brings us back to that earlier point. If these models learn formal structure so well, and if that helps bridge the gap to informal reasoning, could we be looking at tools that don't just verify math, but actively help discover new mathematics?
Could a model like Kimina-Prover, trained on the rigor of formal systems, eventually become a collaborator for mathematicians or scientists, suggesting new proof strategies, maybe even helping formulate new conjectures or theorems?
It's a provocative thought, isn't it? It feels like this line of work isn't just about making AI better at one specific hard task. It might fundamentally change how AI interacts with fields like math, logic, and formal verification fields built on structured, rigorous thinking.
Definitely feels like a significant step. This Kimina-Prover preview is certainly work to keep a close eye on.
Agreed. The potential here is really exciting.
Well, thanks so much for walking us through this fascinating paper. Really appreciate the insights.
My pleasure. Always fun to discuss cutting-edge work.